Okay, I'm gonna hide the floating. Okay. All right, so welcome back. So we'll talk about the first part is the fundamentals. So we'll move to the second part is the system. So I'll give you a little bit more detail, but won't be the technical details about the key component in the system aspect, including the modeling. How do the modeling? What do the sensor do, and how do a control? And also talk a little bit about programming. I believe uh, my undergraduate the graduate assistant from Tao will talk a little bit more this afternoon about how you actually can do the programming in kind of environments, and he can also talk about how to set up environment if you want to try uh, some of the stuff on your own. Okay. Let's see. I want to make full screen. So let's talk about first start with the modeling aspect. So what is the modeling trying to do? So modeling the main idea of modeling is try to understand the relationship between the behaviors and motion of kind of a robot and the control input. You actually have a model to tell if I given certain input, what is the output. So that's if you have taken the control system, that's the kind of the model of the control system. You can have a differential equation. You can have other methods to actually describe the relationship. So here is an example about robotic arm. For example, robotic arm, you normally given is a manipulated geometric parameter. For example, you have different links, right? There are certain angles for the robotic arm, and that's kind of input. You can control that. The output will be the position orientation of manipulator. For example, robotic arm trying to reach an object, you actually have to design to actually specify what kind of angles, let's say what is the angle of this guy, what is the angle of this guy, there's this angle and this angle and this angle, so that this can reach this object. So that's kind of what modeling trying to do. Okay, so for the robotic arm, the input, like I say, is a kind of geometric parameter like the angle typically, okay? And the output will be the position, like ending point, where is this point? And also orientation. Orientation is where it's pointing to. You could point it up, point down, point in directions. So let's say you want to pick up an object over here, you probably want to point down, not point up. Okay, so that's sort of what the modeling is trying to do. It's trying to map between the geometric parameters and to the actual output. So when you design your control algorithm, you just don't have to specify the position and orientation of the element. You actually have to design to control your parameters. So that's what the modeling is trying to do. Okay. We'll also talk about forward dynamics and inverse dynamics. So forward dynamics this is also for robotic arm. So you're normally given the joint angle and the link geometry, like the angle and also length of the link, and try to compute the position orientation of the end effect relative to the base frame. This is kind of forward because you're given the angle, trying to compute what's the position. So the solution will be try to use the kinematic equation. There will be the linear transformation. I don't talk about technical part aspect. You can check it out. The linear transformation, which is a function of the joint position and specifies the end effect configuration in the base frame. Okay, there's kind of relationship we can actually derive using geometric relationship. That kind of equation you can use to actually give angle, geometric, link geometry. You can compute the position and the orientation. Okay. The inverse kinematic is a little bit different. It's kind of goes the opposite way. It's like if I'm given a position orientation that I want my robotic arm to reach, for example, relative of the base, this is my base, and I want to compute all possible set of joint angles and link geometry, which could be used to attain the given position orientation and effects. What that means is I want to reach here at this point. Let's say I want to pick this object over here. I want the position to be here, and I want the orientation to be pointing to north, a little bit to the west, I believe. And then what kind of angles I should give, like theta 1, theta 2, and theta 3, so I can reach that. The solution may not be unique, which means you could have multiple solutions that can give you the desired ending effects. For example, you want to point to the direction and at this position, okay? The typical solutions include the analytical approach. It's kind of opposite of what I mentioned in the previous one. It's just opposite one. You're trying to figure out the solution. The other one is called geometric approach. It's projecting the arm configuring on a specific plane and use geometric consideration to obtain the inverse kinematics. You want to kind of find a relationship in a geometrical way. The hybrid is trying to synthesize in the analytical and geometric approach. So I didn't talk about the details, but you can sort of imagine what inverse kinematics and also forward kinematics trying to do. The forward kinematics trying to say, hey, if I give this angle data, what is my ending, the position and the orientation of the end effector, okay? The inverse kinematics is, hey, I want to reach a certain location, a position at a certain orientation. So how would I pick the angles over here, okay? That's called inverse, okay? So inverse typically can be challenging, a little more challenging because this one, you have a unique solution, you can figure out. Well, the other one, inverse, you may have multiple solutions associated with one particular configuration of the ending effector, okay? So that's for the robotic arm, okay? The second one is car-like robot. So it's like if you're working with typical mobile robots, even for your car, the car we're driving is called a car-like robot. It's like a mobile robots. What typically do is we are giving, so when you drive a car, you know you will control the moving the speed, the forward speed, and also you can turn. The only two control you can have is you change the speed of a car, and you turn. That's what you give. And the goal is try to compute the future position. Like if I drive at a certain speed and turn at a certain velocity for it, turn at a certain rate. So and a given position at an initial position. So can I kind of compute the future position along the way? So that's kind of what the modeling part is trying to do. So the solution that people have proposed, including kinematic models, dynamic models, I'm sorry to go back to that. Okay, it's not a solution. Is we computed the simple model we use to compute this future position. We can use a simple kinematic model, and we can also involve the dynamic model. Dynamic model is more complicated than kinematics, which means dynamic model you don't control the velocity and the angle directly. You only control the acceleration and angular velocity, which makes it a little bit difficult to compute. Okay, this is the dynamic model. The kinematic model means you know your speed. You can change your speed as you want, and you have angle of the robot. Okay, and the solution can also have to consider non-harmonic constraint. It can move sideways, which means your car you cannot move to this direction or to this direction, which means you cannot move sideways. You drive a car, if you want to move like the 90 degree, you cannot direct change your car 90 degree. You have to rotate and change your car 90 degrees. That's kind of non-harmonic constraint. That's why the robot, if you remember in the introduction, the first when I mentioned about a circle-like motion, because for car-like robot, the one common behavior is you move like a circle, you turn around like a circle, you cannot directly turn backward. You have to turn around by taking a circular maneuver. So that's why circular kind of motion is also a very basic maneuver for robot. Okay, so this is like for the 2D, you can see that one, right? For 3D, this is for aircraft, it's much more complicated than the 2D. The aircraft, you have 3D, you have X, Y, Z. Now this one, you only have X, Y, okay? I didn't provide the equation associated with the car-like robot, but they have 2D, you have X and Y, basically, right? Now here you have much more complicated. You have your position, your row PGR, the XYZ, and you also have row PGR, right? So this is more like the for the aircraft, what kind of model you could imagine. I don't want to talk about all those numbers over here. It's kind of complicated. What I mean over here is the 3D aircraft can be much more complicated. Well, within this, it can be really important because you actually can see how this input, you have like UVW, this kind of control input, how those, you also can convert this one into sort of the thrust, the bank angle, all the kind of inputs, and that will affect your row pitch angle and as well as your position eventually. So this will be really complicated. The reason the model becomes so important because this equation can tell you, hey, if I give certain input, you can see what's going to happen for the output. Without having the model, we don't know how the input will affect the output. Okay, so that's what the modeling is trying to do. Okay, so like I mentioned before, what the modeling is trying to do is try to provide an abstract representation of the relationship between the input and output. So this abstract representation can be in terms of ordinary differential equations, can be in like the Markov decision process, for example. That's what I talk about in the decision making part. So those abstractions is important because it can tell you if you take certain action, I will tell you what kind of output you expect. That's exactly when you do the navigation, for example, you're starting from A to B, and we want to know exactly if you take action, and the robot will behave in a certain way, and we'll see the output will tell us if it's moving towards a goal or moving towards is not moving to the goal. Especially we talk about the path planning, because if we plan the path for the robot to take, and if we take action, we can compare if the actual robot behavior will match the path we selected or we actually planned. If it does match, which means we can continue. If not, we need to just adjust the control inputs, okay, or the algorithms, okay. So it's a great starting point for the control design because you can, by using the analytical relationship, you actually can design control input. For example, you can use a PID, although PID is not a model-based, you don't need to have the model. But the other method, you need to have the model, for example, to actually design your control algorithm. Okay. So often you can have a good model, for example, in the previous, like the aircraft model, but it may perform poorly in the real world environment. For example, here, this model is good for the aircraft model, but it doesn't involve the wind, as you can see. So typically we don't have, it can become much more complicated, especially if the wind even is not a constant. So how do we actually provide a more accurate model? That's kind of challenging, okay? The other one is the model does not, I haven't talked about the model including the environment because this is only model we have for the aircraft. And you can, as you can imagine, we probably also have model for the environment. For example, you have a model for the wind, you have a model for even the temperature that will also affect the dynamics of aircraft. Okay, so like I said, aerodynamics can change dramatically due to wind and heat. So it's also important to model other parameters. I didn't talk about over here. This doesn't belong to the model of the robot, but it's important if you talk about specific area, you model the environments as well, okay? So robot dynamics need to adjust subject to different terrains, okay? Even for this, the ground robot, the typical, we haven't taken a model for that, but for different terrains, the behavior or the model may be a little bit different. Okay, now let's move to the sensors. Okay, that's about the modeling part of sensors. Sensors are used to detect event and change in its environment and send the information to other electronics. Very likely is a computer processor, which can process the data. It can provide important measurement of the vehicle state. For example, if I use the GPS, actually can detect the location or the position, even position, velocity, acceleration, even acceleration of the vehicle, which is important. If you can see over here, for example, if I drive a robot from A to B, for example, from A to B, how do you know if it's on the right path? You must have sensors which can tell you if you are moving along the right path, right? That's what the sensor is trying to do, okay? Of course, keep in mind the sensors normally can be noisy and inaccurate, which means the measurement may not be accurate all the time. For example, even if the robot is running at a speed of, let's say, 20 miles per hour, when you actually get a measurement, it could be 19.5 or it could be 21 miles per hour, okay? Okay, the type of sensors we typically work with in terms of robot, we have image sensors, including RGB and IR infrared. RGB, all people in recent days, you can have RGBD, which can provide a one-dimensional distance measurement of from the images. Okay, IR infrared for for the night or for the kind of other operation you want to detect the heat, for example, that's more important. Also, we have motion sensors, including the IMU and the GPS. We have detection sensors like LiDAR and radar, and they actually the sonar, for example, they can detect the obstacle in the environment. We also have thermal sensors, and we may have different type of sensors. Okay. Okay. when we talk about sensory data, we also talk about sensor data processing. How do we process data from the sensors? As I mentioned before, because the sensors data can be noisy, so we would include important techniques to actually process the data in the right way, so we can get the right data. Okay, if it's not incorrect, it's not correct, then which may not provide valuable information for the subsequent like control or reasoning aspect, planning aspect. So sensor data, a couple of important techniques for sensor data processing, including the data filtering, which is mainly to actually filter out all the noise. It can be high frequency or low frequency noise, including, for example, Kalman filtering, extended Kalman filtering, the particle filtering. So that's kind of techniques. There are kind of other techniques as well to filter out the noise. The second key tool is called sensor data process cleaning and denoising. For example, this Kalman filter may not be able to filter out all the like the spiky data, like spiky errors, but for spiking errors, so we can use data denoising and cleaning. You can sort of see if they are very abnormal readings from the sensor, you actually have to remove it. You don't need to include it in your data at all, right? Also the sensor data dimension reduction, because a lot of times we have a lot of data, which may not help us because we have too much data to process, especially for real-time processing, because that's important for robotics. So how do we reduce the size of data so we can fit our algorithm? First of all, second one is try to fit the decision cycle. Typically will be pretty short, okay? The last component is the sensory data processing, which means the sensor data fusion, which means you probably have data from multiple sources, right? So how do I actually fuse the data from different sensors? For example, you have a different view of the object. How do you fuse the data from different sensors so you can get a better idea to actually get a better idea about the object? That's kind of sensor data process, data fusion. Okay, so that's about a sensor part. Okay, the next one is about the control part. Okay, the control part is you actually get the data from, you have a model of the robot, and also you have the sensory data, the sensor data to tell you where you are, for example, and also your velocity, your position, kind of data you have. The next one is what kind of action should I take, right? Assuming, of course, I have some goal that I want to achieve or some mission I want to achieve. For example, you move from A to B, and now your sensor tell you are at a certain position on the path to B, okay? And also you have your model telling you, hey, if you would take certain action, what kind of output you would imagine, okay? The next part, important part, will be what kind of control input I should give so that the robot can take certain action to achieve the goal. That's called robotic control. So at least a number of methods, at least a number of robotic control methods, including the PID. I think this is probably most well-known one. If you know that, if you take the integrated control course, you have proportional, integral, and a derivative control. Okay, and also the second one is receding horizon control, also called a model predict control. And for robotic manipulator, we have inverse dynamics control, and also have potential field, behavior-based, virtual structure, learning-based control. Okay, the learning control become really popular right these days, especially using the reinforced learning methods. So I give a brief introduction to that part. I wouldn't talk about too much detail. If you're interested, we can also provide a little more about what this part is about. Okay, and this becomes more popular. Okay, of course, this method also played an important role in the current generation of robotics. Okay. All right, so I think that's all covered about the robotic control. Last component for the system is about programming. Actually, how you actually make it work, because you can have modeling, you can have the sensor, all the stuff, and also control in all, they're ready. But how do we make it work together? And especially, how do you have a kind of system that you can play with, either in the virtual environment or in the physical world environment? Okay, so the robotic programming talk about, how do I actually do the programming so the robot can do the stuff that I want, okay? So one of the most popular one is called robotic operation system, which is called, people call ROS, is a flexible framework for writing robotic software. So it's a very good one to for you to learn if you're interested in this area. It is actually a collection of tools, libraries, conventions that aim to simplify the task of creating complex robot behavior across different type of platform. Actually, the nice thing for the ROS is it supports a variety of robotic platform, not just one. Okay, I think I'm going to show you what ROS is about. In the let me see if I can you see my screen?
Yes.
Okay. All right, that's great. Okay, so this is a page for the ROS. As you could see, this is like, I don't want to read all the stuff over here. So here's also a video. I couldn't play it because the network error or something like that. Okay, so this one,
Professor, I think we cannot see the screen. We only see the slides.
Yeah, we can only see slides.
I see. Okay, let me see if I do this. Does it work?
Yes, we can see you.
Yes.
Oh, I think I only share slides. Okay, now works. Okay, so the ROS, it's pretty popular one. It's like if you work with Windows, you work with Linux, that's operation system. Robotic, they are supposed to be working as a robotic operation system. Okay, but not as nice as Windows, Mac, or Linux, but it's pretty nice. Okay, so what it does, it tries to provide a unique platform that's different. You can work with different robots. It provides a lot of functionalities and tools that you don't have to develop because already developed there for you, make our life much easier to do. Okay, so I encourage you to actually let me see, to actually take a look at this if you're interested in robotics. Okay, let me see. Go to the next one. So let's talk about what is the key components that ROS provide. Why it's kind of very nice. Okay, so ROS provide a couple of components. The first one is communication infrastructure. It basically helps you to deal with all the communication between the robot and also your computer that you process. Let's say you get data from the robot. How do you get that? It's already been done by the computation infrastructure. It supports the publish and subscribe and anonymous messaging passing, reading and backup messages, request response, remote procedure calls, and distribute parameters, which means you don't have to worry about all the get the information back and send it to the robots. Okay, which is pretty nice. And also provided robot specific features like standard message definition for robots, and geometry library, declaration language, and other kind of components. Okay, it can provide different components that you can play with. So this is a very popular ROS simulation environment. So this is like, it's not the actual environment, it's a physical environment you can play with. You can build your map, you can actually run, and you can initialize your robot and see, you can trust your algorithm, see how it works in the virtual environment. Okay, this virtual environment is called Gazebo. Okay, you can actually play with it. So this is what Gazebo provides. Okay, it provides dynamic simulation, advanced 3D graphics, sensors and noise. You can do that, and I have robot models and TCP/IP transport, even other tools. Okay, you can check this website to get more information about the simulation environment, Gazebo simulation environment. Okay, the other one is when you're interested in working with the reinforced learning kind of learning-based algorithms, or OpenAI is pretty, it's a non-profit organization that provide a different environment that you can also play with. And this one's the OpenAI ROS. Let me see if I have opened already. So it's an OpenAI reinforced learning structure to train the ROS based on robots in Gazebo simulation. You actually can use a lot. So this guy, the ROS does not provide of the learning algorithm that as many as this, the OpenAI environment. So you actually can leverage both the OpenAI environment as well as the ROS, the simulation environment, actually get a trained using the reinforcement learning algorithm, but you're based on the Gazebo environment. Okay, so let me show you. I think I have the environment over here. Okay, this is the OpenAI ROS environment. So you actually can make your OpenAI reinforcement infrastructure train on the ROS-based robotic in Gazebo simulation environment. Okay, so here's how we do that. I don't want to talk about too much detail about this. You can actually follow the instruction to set up and try try to train your algorithm, right? If you're using reinforcement learning algorithm and using the Gazebo simulation environments. Okay. So the other one is called raw simulation. That one is more related to the air vehicles, called air sim environment, which is a simulator for drones. Not mainly, you can also, mainly people use it for drones, but you can also use it for cars and others. The nice thing for this one is built on Unreal Engine. So if you know Unreal Engine, so an Unreal Engine is more like a simulator. It's used for a lot of games. When you play the games, right? They use the Unreal Engine. The latest version of Unreal Engine, I think the Unreal Engine 5, or I think it's 5. So they actually try to mimic the real world environment. So old version of Unreal Engine, they are more for provide a static environment, which means if you drive a car to a certain point, the wind, other condition will always be constant, will be the same. But the new version of Unreal Engine, it will be different. Like you fly drone from A to B and you move to certain location, even if you fly to the same location, at different time, the environment will be different, will be random, which is more practical. We consider real-time environment. So that's kind of very, very nice to have. And plus, it is open source across platform and support software in the loop simulation with popular flight controllers such as Pixhawk, LG Pilot, and hardware loop with Pixhawk 4. So I think it's pretty nice to play with if you're interested in more like an air type of robots, okay, air vehicles. Okay, I'm gonna show you the AirSim. This is the web page. This is the site you can check if you're interested. You actually can fly around it. So one of the things the AirSim does not do is it won't involve the model agent, for example, in the environment, I guess, right now. So you're almost static in the environment. For example, here, it's kind of you're flying around, you move around, the car does not move. So when you talk about the multiple vehicles, they could all move along the road. It may not work well in the open AI and the AirSim environment, but they may provide updates to support those kind of capabilities later on. Okay. So in terms of programming, so a quick and efficient way to do the programming is Python. I know a lot of you have used the C++, which is nice because that's good for real-time processing. However, Python is more efficient. Okay, it's quick way for you to do the programming of the code, and also the nice thing I'll talk about Python is also good for you to work with machine learning and the deep reinforcement learning algorithm, because a lot of these packages are written in the Python, so it's easy. But doesn't mean you cannot not use other programming language, which is fine. I think nowadays it's pretty flexible in terms of programming languages. Okay. In terms of if you use Python, one popular tool, kind of the framework you want to use is PyTorch. One way, you don't need to use it. Okay, that this PyTorch is an open source machine learning framework that accelerates paths from research prototype to production. So let me show you what it looks like. Okay, just show you all this. Pretty simple. Just check the PyTorch. You can see, right? You can install this one. You can click install on your computer, and it has tutorial for you to do many things, including this is what it includes. Okay, and of course you can, if you have different operating system, OS or Mac, other stuff, you can also have different versions you can install. Okay. So and another one you want to try install is Anaconda, which is an easy way to manage the working environment with right package of data science, which means you have different versions of Python, for example, and you require different version of, you start different type of stuff. The nice thing for Anaconda is try to manage your environment in a way that you can install different environments. And this environment can be conflicting if you don't have Anaconda, because you have a version, let's say you want a Python 3.2.5, but then for some other experiment, you want a 2.1, for example. Then your Anaconda, you can create two different environments with two different type of versions of Python, which will be okay. It's very easy to manage. So Anaconda, it's pretty simple. I think it's just self-explanatory. You can just download it and install all the stuff. Okay. Over here. So here's a website. I don't want to talk about it too much. I'll give you can just check online to see how you can install on your own computer. Okay.
I strongly recommend everybody use PyTorch because that's a trend right now. And especially the environment setup is much easier than Anaconda. So I hope that everybody choose PyTorch in this group so you can discuss with each other, learn from each other, instead of I use this environment, the other student use, other environment, then it's pretty hard for you guys to learn from each other, right? Okay, go ahead.
Okay. So how to get started? So I know a lot of things I mentioned already, especially from the programming component. What I suggested to install package on your computer first. So it can be time consuming to install right version configure the system because you don't know what specific package you have to install. Okay. And you can take your time to try, that's kind of beginning stage, trying to figure out how to install all the packages. And the next step is once you install the package, you can actually conduct some simulation in the virtual environment. So generally, you don't have to set up the robot at certain position because you already provided the location, all this information, like the sensory data is already built in the simulation environment. So it's less complicated. Then you can connect to the physical robot. So I don't know how many of you would be on campus, but we do have a lab that we do have physical robots. We have drones, ground robots, all stuff that you can play with. So after finishing, we don't suggest you directly work on the physical robots. We suggest you will start your work in the simulation environments, and then you connect to after that is done, showing that it works well, you can connect to the physical robots. This can be challenging given different robotic system. And even a lot of times the issues may not come from your algorithm at all. It comes from another component like hardware communication. It does not connect, okay? Another thing that I want to emphasize here is in the virtual environment, it's easy to connect to multiple robots at the same time because that's kind of in the virtual environment. However, in the physical environment, it's not easy to connect to multiple robots at the same time because the communication channel would be issue. You have to set up that one. Either you can split your communication channel into different like the CDMA kind of type, or you have to just initialize a different threads for the communication, which may be challenging, okay, in the real world environment, especially you need to send the data back and forth, okay? So the physical robot typically can be very challenging, okay? The last point I want to emphasize, a lot of those code can be found online for you to get started. So you don't have to develop code by yourself, but you can just adapt other code for your own purpose. But it's important to understand how the code was structured and how it was written. So you, in the future, if you want to change your code to fit your own needs, you actually can do that. So in terms of working with the robot to get it started, I don't have more suggestion other than having more practice, because it takes time to actually know how everything works. Okay. All right. So that's about part 2 of my part 2. So I don't know if you want to stop or should I continue?
Let's stop here so we can have short video.